All right, hello everyone. This is Tips from a Hacker on License Checking. I'm Chase. I've spent the last few years working various places in information security on projects that include tasks like malware analysis, software reverse engineering, and vulnerability analysis. So despite the fact that I am not someone who cracks or uses cracked audio plugins specifically, I have spent some time learning essentially the same skill set for the sake of competitions and professional work. So I think I nonetheless have some expertise to rely on with respect to this issue. So when I'm done with this talk, I hope that you will understand the tools and approach of most crackers. I hope you'll have some idea about how to implement a license checker. I hope that you will know some common mistakes to avoid, which, if made, can make it much easier for crackers to bypass your copy protection. I hope you will additionally know some techniques to harden your copy protection. I will not, unfortunately, be able to provide an uncrackable scheme for everyone to use. Such a thing is impossible. But I can provide a sort of mental framework for people to use when designing their own schemes, and some general advice on how to harden those schemes and make it more difficult for people to reverse engineer them. So first of all, what is license checking or copy protection? As many of you have no doubt experienced, the first step after downloading an audio plugin or other software is usually to enter some sort of authorization key or license file. And as I'm sure you can no doubt infer, the purpose of this is to ensure that those who have purchased it are the only ones who can use it. There are, however, crackers who will alter the software to bypass these checks and distribute them widely on piracy websites and forums. So what we want to do is make this task more difficult. Okay, so there are a few approaches to copy protection. The first is to not bother with it or to implement minimal license checking. This can work particularly for small companies with cheap products. If your software is only a few dollars and you don't have a lot of time to invest, then users might rather pay for it than go through the work of pirating it. And if your user base is small, your product might remain under the radar of the more competent crackers. But as soon as there's sufficient demand for your product, it will inevitably be released on piracy sites. And so, another option that's commonly opted for is to contract a company like Pace to do it for you. I'm not going to recommend against this option. It's highly unlikely that your copy protection will be designed as well as theirs. But there are some downsides. The first is, the large number of products that use it means that, many crackers will be targeting this scheme. And when the, latest generation of it is inevitably cracked, all the plugins that use it might be cracked also. And you also just might not want to pay them. And so the last option is to roll your own copy protection. This will not be the best option for everyone. One of the pros is that, your software will only get cracked if it gets targeted specifically. It won't cost you anything except time. But the main risk is that your implementation might contain, one of the myriad of mistakes that can make it easy to crack. And so I'll leave it up to your judgment as to whether this is the best option for your product. But my presentation will be focused on this final option. So I think it's well known at this point that no copy protection is perfectly secure, and that if someone skilled enough is willing to spend enough time on your product, it will eventually get cracked. So you might ask, what is the point of investing in copy protection in the first place? So I think having even a mediocre design can significantly raise the bar with respect to who can crack your software. So if your product isn't in comparatively high demand, the expert crackers might not get around to it. And so it might be a lot longer before it gets cracked because the beginners are unable to do it. Even if it does get cracked, I think you can reduce the frequency at which this happens. You can find various testimonies on the Juice forums or KVR forums of people who are having their products recracked within a few days of every major update. A good license checking scheme can make this process take weeks or months, which means that the cracks will be increasingly out of date compared to the legitimate versions, and thus it'll look less appealing to users, And it'll look less appealing to the crackers, who might anticipate a much more difficult job in reverse engineering your software. I would also propose that if everyone across the industry makes their plugins, just a bit more secure, it could significantly reduce the rate at which plugins are cracked across the industry, because now most schemes, are relatively basic or make, basic errors. That means it can take minutes to crack them. Whereas, even a slightly better designed scheme could take, significantly longer. So over the next 40 minutes or so, I will present some tips that I hope will, help everyone who's interested make their plugins a bit more secure. So the first thing I want to discuss is the Cracker Toolkit, namely the tools and techniques that the crackers use. Most of you are probably developing your products in a language like C, C++, or Rust. These languages are compiled from the code you write down to an intermediate representation like LLVMIR or MLIR, and then finally down to the assembly language for the target platform. And since the cracker doesn't have access to the source code, at least I hope, they must either, one, find a weakness in the scheme that allows them to generate valid licenses, or two, alter the compiled binary to bypass these checks. We'll take a look at both of these, and often crackers will do some combination of both of them. So as far as the tools that crackers use, the first broad category includes survey tools. So this could be tools that allow them to dump the strings in the binary, to dump all the detected function symbols, to generate diffs between two different versions of a binary, etc. It may also include disassemblers, like Binary Ninja, Ghidra, IDA Pro. The purpose of these is to lift parts of the binary file into assembly, and then these tools can usually also run various analyses on that assembly to recover things like function starts, the control flow graph of some function, cross-references between code and data, etc. They may also use a debugger, which, in addition to the above tools, can include things like GDB or LLDB. Many of you have used debuggers to diagnose things like segfaults or other problems with your software, but these can also be used by the cracker to recover information about some software while it's executing, which is often easier to do than by just statically analyzing it. So in a minute, I'm going to demonstrate various ways a cracker might approach your software. There are nice graphical tools like the ones I mentioned that most crackers will use, some of which will cost thousands of dollars. But for all the examples I'm going to show today, I've chosen to do everything in the terminal. This can make the reverse engineering a little harder, but I want to make sure that nothing in this talk can be used as a tutorial by a beginner cracker. And so hopefully the way I present these examples will help you all understand how to better protect your software and what kinds of weaknesses you need to avoid. While at the same time, someone who isn't already skilled won't be able to follow any of the individual steps that I do. Yeah. Okay, so to make sure all this is clear, I'm first going to show how one might use a debugger or disassembler on a small program. And then after that, we'll get to some basic license checking schemes. All right, so if I go to my terminal, you can see I have here listed in the directory a example binary and a main.rs. We can take a look at this main.rs file, and you'll see at the top here that we get the list of arguments stored as a vector. We then check to see the number of arguments passed. If it's too few, then we print the usage information. And if it's the correct number, then we will check the first argument against the string 1234, after which we will, print if the password was correct or incorrect. Okay. So if we exit out of this, we can, run the example binary. And then we can pass it a string like 1111, which in this case, it will print incorrect password. And so now what we're going to do is we're going to disassemble this binary to see how we might go about discovering this if we didn't have access to the source code. So we'll first run some analysis on the binary. And then from our tool, we can do things like show the hex dump of any part of the binary. And we can scroll around that hex dump. We can also list the strings if we so desire. We can even print the functions, which in this case, I'll filter it for the main function. And then we'll copy that and seek to it. And then once at the main function, we can print the disassembly, as I've done here. And these are all the individual assembly instructions for that function. We can also display the control flow graph, like I'm doing here. And if we, sort of scroll down through this control flow graph, we come to what looks like the, important comparison block. So if you look at this sort of top center block, you can see that there's a compare to the value pointed to by RAX and some, number that's been hard-coded. And then based on this, you can see the sort of branch to the left and the right, true and false, between, blocks that look like they're doing something related to printing correct password or incorrect password. And so, we can just at first look, guess that this is the relevant compare to the password, with the relevant printing. So next, before we finish cracking this, I want to take a look at debugging it. So I'll reopen this in the debugger, passing it the arguments 1111. And then I can add a breakpoint at the main function I copied earlier. At the main function I copied earlier, and then I can continue to that. And you can see I've now, now the debugger is stopped at this particular portion of the code. I can step through the individual assembly instructions like so, and even display more information about the memory. Like you can see at the top there, I have the stack, and then below that, I've displayed all the registers. And if I step through this, you can see the stack and the registers changing according to the instructions. So if I go back to the control flow graph, I can also step through it until I get down to the block that we saw earlier with the relevant compare. And I can do one more step through that, and then I'm at the compare between what's pointed to by RAX and this hard-coded value. So the first thing I'll do is I'll print the value pointed to by RAX, and you can see that's 1111. So we assume that the value it's being compared to is the correct password. So what we'll do is we'll just copy this 34333, so on and so forth value, and then we'll print it in its various formats. And you can see here that if it's formatted as a string, it's equal to the value 1234. So from this information, we can assume that we've identified the correct password. So we'll just continue, and you can see what we entered before was the incorrect password. But now if we run the example binary with the newly discovered password, we see that it's correct. Okay, so obviously, this wasn't, an example with a, license checking scheme that you might see in the real world. The point of this was just to illustrate the general reverse engineering process, what a disassembler is, what a debugger is, and hopefully this will allow you to follow the examples that I do later with more advanced, against closer to real world license checking schemes. All right, so next we're going to take a look at our first copy protection scheme. In deciding what kinds of designs I should look at for this talk, I took a look at the JUICE forums to see what people were already using and what was being recommended to newbies. Most of the designs I saw involved using a RSA private public key pair to secure the license in some way. But unfortunately, I did also see attestations to common misuses of RSA and the effects of the subsequent cracks. So this first example I'm going to show is a kind of worst case scenario in terms of the copy protection. And I'll show how misusing RSA can make it trivial to crack a plugin. Okay, so if I go back to my terminal, you can see in this directory, checker 0, we have a checker 0 binary and then an encoded license. I can print a hex dump of that license, and you can see it at the moment to us just looks like random data, and so we can assume it's encrypted. So our first step will be to disassemble the checker 0 binary. We'll run our analysis again. I'll wait for that. Okay, and then we can seek to the main function. So if we go to the control flow graph and scroll down through, you can see there's this call to a check license function. And so normally we'd probably proceed by reverse engineering that. But in my quick scroll through, I did notice something at the top if we scroll back up, which is you can see our tool here has detected a reference to what looks like an RSA private key of some kind, which is bad. You should never see the private key distributed to users. And so we will first try and dump this private key by using a survey tool to dump the strings, and then we'll just filter it for the header of that key. And then you can see we have the private key here. So I'll just copy that, put it into a file. And paste. All right, and we have our private key. So based on the fact that the private key was embedded in here, we can guess that the developer in this case made a relatively common mistake, one that I have seen on the Juice forums, but one that makes it trivial to crack this plugin, which is that they have used the RSA private key they're using the RSA private key to decrypt the license, and they're using the public key to encrypt the license. The problem with this approach is that the way RSA works, you can at any point generate the public key from the private key. And so in order to break this scheme without ever having to alter the binary, all we need to do is take this private key. We can use it to decrypt the license if we so wish. And we can also use it to generate a public key that we can then use to generate forged licenses. And so I'll show that process in 1 second. So you can see I can get the hex dump of the encoded license. We see that it's encrypted. And now I'll proceed to use OpenSSL to decrypt this into a plain text license. And if we cat the resulting file, you can see what we have is a plain text license that includes the username and expiration date. And so what I'll do is I'll edit the plain text license to include, some forged information, from some user, and I'll extend the expiration date because I can. And then what we'll do is we'll generate the public key that we need from the private key in order to encrypt this to be, what looks like a valid license. So we have our public key, and so we'll now use that public key to encrypt the forged license. And then once we have our new .encode, we will simply switch the old and the new licenses so that we can test it against our checker. So we'll run our checker, and you can see it detects that it's a valid license with the username and the new expiration. Okay, so notice that in this example, the cracker didn't need to change the binary in any way. They were simply able to generate valid licenses, which is why this is sort of the worst case scenario, because users can simply download the latest version of the plugin from the official website and then authorize it with a forged license. Yeah, so this is the worst possible case. So I expect that most of your schemes will not contain this mistake, but it is something that I have seen before, and it's why I thought it might be useful to present it. Okay, so our next example, I'll show a more proper usage of RSA. And I suspect, based on what I've read on the Juice forums, that some variation of this scheme is quite common. And so hopefully this example will help explain the weaknesses that many of you might have in your current copy protection. Yeah, okay, so a bit about this example too. In addition to using RSA properly by embedding the public key and using it to check a signature, it also obfuscates the public key in various ways to make reverse engineering more difficult. But we'll see that despite all this, the scheme ends up being quite weak. And hopefully this will illustrate, the kinds of weaknesses that copy protection schemes can have, even when some thought was put into their design. And then after this, we'll discuss some better ways to harden your schemes. So just a quick note, so that it's sort of easier to follow when I'm reverse engineering it later. The cracker wouldn't know this. This is something they discovered by reverse engineering. But the way that the developer obfuscated the private key in this case, or the public key, sorry, the way they obfuscated the public key in this case is by splitting it into 8 different parts, storing these parts at different places in the binary. And then each of these pieces is encrypted at compile time and then decrypted at runtime. So that when the public key is used to validate the signature, the license checking function will first call each of the functions needed to decrypt the data that's stored statically in the binary and then combine all 8 bits of data to reconstruct at runtime the public key that it can then pass to the relevant functions to verify the signature. Okay, so we will, if I go back to my terminal, take a look at how we might approach this scheme. Second. Yes. Okay, so in our checker1 folder, you can see we have a checker1 binary and then a folder that contains the keys, which in this case, there's a license.txt and then an encoded signature. In your real schemes, you're probably going to want to encode or encrypt both of these into a single file. But for the sake of this example, I have it as 2 separate files just to make this example easier to understand. I can cat the license and dump the hex of the signature, so you can see the format of both of those. All right, and then if I run the checker, you can see it detects that there's a valid signature. Now what I'm going to do is I'm going to go to the license and I'll change the name to something invalid. And then if I go back, if we run our checker, you'll see that it detects an invalid signature. Okay, so now as the cracker, what we want to do is make it detect a valid signature even though it's currently invalid. So we'll start that process by opening our disassembler and running some analysis. And the first thing we notice is that if we list our functions, we don't have all those nice symbol names like we did before. The symbols include, in a binary, include many things, including the names of functions. If you're reverse engineering something, and you're very lucky, the binary might include all the function names, which makes it, much easier to reverse engineer. Many frameworks by default will strip symbols whenever you compile in release mode as opposed to debug mode. But this is not always the case. Rust, for example, includes symbols unless you explicitly specify the appropriate flag. I also mention this because I've seen it recommended online that people include symbols even in their releases, so that users who experience crashes of some kind can upload a core dump, and then you can more easily trace the source of the crash. I'm not necessarily saying that you shouldn't do that, but there is a significant security trade-off in that it becomes significantly easier to reverse engineer a binary with all the function names in it. Okay, So if I go back to my disassembler, I can dump the strings because, we want to find some string that might be an irrelevant function that we can start reverse engineering at. So if I scroll up through this, a little bit more, you can see this invalid signature string up here. That looks like something related to signature checking. And so the next thing I'll do is I'll just copy that address, and then I'll find all the cross-references to it, which in this case there's one. So if I seek to that, I will find, a bit of code. And so I'll scroll up to the top of this, what looks like a function, and I'll just define a function there since it wasn't detected before. And then rename that to checker. All right, and then now, I can look through the control flow graph, and you'll see up here at the top are all the calls to, what we know, but the reverse engineer would have to discover by reverse engineering further. These are all the functions that reconstruct the public key from the encrypted data in the binary. So, if we were reversing this, we might go look through these and we'd see that, this is, looks pretty complicated. A lot of these functions are quite large. So we might come back to this later after we've done some more triage. So we'll continue this by just printing the whole linear disassembly of the function. And looking through, we see it calls various strings and it references various strings, calls various functions. But perhaps most importantly, we see this call to a digest verify final function. And if you've worked with crypto before, you might recognize this as the final step to verifying a signature. And so what we'll do is we'll seek to this address and look at that basic block. And you can see here, there's the call to that final function. And then it compares the return value, which is stored in EAX, to 1, which in this case is going to be true. And then it branches, based on true or false. So we might venture to guess that what's happening here is this is the final step of the signature verification. And then based on if the verification indicates validity or invalidity, it will branch to the, success or failure conditions. And so what we might want to do is alter the code here in some way or patch the code here in some way so that it will succeed when there's an invalid signature. So to do this, I will go to the relevant instruction and, there's various ways you could patch this. But for the moment, what I will do is simply replace the compare to a 1 to a compare with a 0, so that it will succeed when an invalid license specifically is passed in. And I will paste the relevant address. Okay, and you can see that instruction was changed. We can now exit out and run our checker, and you can see now it detects that the signature is valid. And if we go into the license and change it to some other user, and then exit out, you can see that yet again it is detected to be a valid signature. So what was the problem with the previous example? The biggest problem was that despite the fair amount of work going into obfuscating the public key, there was still a single branch that the cracker needed to patch to bypass all of it. And they could do this without needing to go through the work of understanding the obfuscated key reconstruction code. In the end, all the work that went into obfuscating the implementation, was irrelevant to what the cracker needed to do to bypass the whole scheme. So how might we improve this system? In approaching this question, I want to first observe that there are at least 2 broad classes of schemes people can use when developing their copy protection system. The first is involves the use of cryptographically secure algorithms. When these algorithms, like RSA, in the previous example, are used correctly, it can be practically impossible to forge valid licenses. But the problem with this is that these systems are often easy to reverse engineer because they use systems that are well known. The reverse engineering tools are able to identify functions, relevant to OpenSSL or some particular implementation like we saw in the previous example. And so it can be easy for the reverse engineer to replace the embedded public key in the binary with their own and then forge licenses for it or something like that. And they can do all this without needing to reverse engineer much of the code. They just need to identify key bits. The alternative is custom schemes, or schemes that combine in a sort of user-defined way a variety of open source algorithms for encryption and decryption. And with these schemes, if the cracker wants to spend the time reverse engineering the convoluted use of some combination of encryption and decryption algorithms or hashing functions, it may be that they can forge valid licenses. But the way these schemes are implemented is usually much harder to reverse engineer because it doesn't use algorithms in the usual way. And so there's a lot more manual work that's required to understand how these schemes work before you can generate or forge a valid license. And so I think a potentially productive approach is to combine these two into a single copy protection scheme. So an example of this might be if you used the RSA key properly, as we saw in the previous example, but simultaneously appended to the encoded key a series of hashes from the license, and these hashes are generated using either user-written hash functions or user-defined combinations of popular hash functions, which are compiled in such a way that the reverse engineer needs to spend a significant amount of time understanding all of this in order to know how to forge each of the hashes that go beside the key. So in thinking about how to design these schemes, I've listed here a set of principles that we can refer to guide us in developing schemes that are hard to reverse engineer. The first is diffusion, which is that we want to spread our license checks over both time and space in the binary. Second is obfuscation. We want to make it difficult to understand how these schemes are implemented. The third is integrity. We want to, when possible, make sure that our integrity checks or make sure that our license checks haven't been altered. Variety, we want to make sure that these checks are different from each other so that they're not searchable or cross-referenceable. We want our checks to be incremental, so we want to check the license in pieces rather than have a single point of success or failure. We want the checks to be isolated from one another so they can't be discovered by following a single path in the control flow or by cross-referencing between them. We want the checks to be integrated with the important code. And then lastly, we have frustration, which is the desired mental state of the cracker when reverse engineering, though there are no guarantees. So first I'll talk about diffusion. We want to spread our checks over time and space. And if you think of the previous, the example I proposed earlier where we have our, RSA generated signature, and then we append to that signature several hashes of the signature, and then append those to the license. And then you can imagine that these hashes are checked in various places throughout the code. You're going to want to inline these checks so that there isn't a single place that is being referenced by all the different checks. And this will ensure that all the checks require their own patches, which creates a lot more work for the cracker. The next issue is obfuscation. We want to make it difficult for the cracker to understand what's going on when reverse engineering the binary. And to do this, you can encrypt sensitive data at compile time, like we saw with the RSA example, although in the end, in that example, it wasn't done in a useful way. You can do things like add fake functionality, unnecessary checks, misleading strings or symbol names. And you can also do things like obfuscate system calls that reveal important parts of the functionality. Like, for example, if you, say, had a random function that determined whether or not you were going to indeterministically evaluate the validity of the license or a hash or something like that. You could, instead of the rand function, which might sort of give away what's happening, you could use the return bytes of a malloc or the time in seconds or something like that. Next, we have integrity. You want to make sure that your code hasn't been changed when this is possible. The best way to do this is to check the hashes of important bytes at runtime, and then these hashes would be calculated at compile time. But this can be somewhat difficult to implement unless you are particularly passionate about this kind of work. And so there are simpler alternatives like on some condition running a bad license through your license checking function. And if the bad license succeeds, then you know that probably the cracker altered this function in some way to make sure that it succeeded even with bad licenses. And you can also do simple things like check the hash of the entire binary or something like that. Next, we have variety. You want to make sure that there's a variety of different checks. Often, even when checks are diffuse, a hacker can find all of these by searching for easily, common bytes between them. And you may want to use different algorithms for each of these checks. And you also may want to, if possible, vary between releases how this is implemented. This might be a pain to change copy protection by hand. I think most of us, copy protection is not the priority. Instead, we want to focus on the core functionality of our plugin. So instead, you might do something like have the elements of the copy protection generated at compile time using Rust macros or C macros, so on and so forth. The point of this is that we want the functionality to vary enough between releases that disabling the copy protection isn't scriptable. I've heard various testimonies that, to the effect of within a day or two of every major new update, a crack is released online. And though I don't know this because I haven't talked to any of the crackers, I suspect that for the more popular plugins that they're releasing updates for often, they've written scripts to disable the copy protection on each version. And if at compile time you vary the copy protection enough, it might be difficult for these scripts to do that, which would force the cracker to do things manually, which would slow down the rate at which cracks can be produced. Next, we have incremental. When possible, you want to do only partial checks on the key so that the failure message isn't immediately displayed. So you might want to, for example, only do a basic check on the startup of the signature of the license, for example, and check the other bits of the license only on rare conditions. So if you had the appended hashes of the signature, like I mentioned before, you might check these on rare conditions like, the 400th prepare call to the prepare function, or, so many minutes after it's been running, or after they save a preset or something like that. And this makes it difficult for the cracker to tell if their crack has succeeded. And so in the best case scenario, the cracker only bypasses the basic check on startup, distributes this to hundreds of users. These users spend some time with the plugin, find it useful, and then suddenly your secondary checks are triggered and they get, a demo pop up and, the full functionality that they had before was taken away. And at this time, they might be motivated to go buy the actual plugin. Next, we have isolation. You want to make sure that the checks of the license and the important data to checking the license cannot be easily cross-referenced. A sort of worst case scenario would be if you had a bunch of checks that were different from each other and they were diffuse throughout the binary, well designed and all that, but they all referenced a single global variable. What would happen is the cracker would, likely at some point list all the cross references to this global variable and then instantly know all the bits of code that reference it. And so in this way, they could easily find all the checks that are buried throughout your code. And so instead, what you may want to do is dynamically resolve these references by calculating at runtime the address of the pointers where the data is stored so that a static analysis tool can't identify it. And you may also want to do things like for critical for like network functionality, for example, if the only time your plugin used networking was to periodically check the license against some data that a server could provide. If your plugin had no other networking code, it would be a pretty strong giveaway to the cracker what was happening if they at some point listed all the imports to your binary and noticed networking related calls. At this point they would find the cross references to those, and then they would notice the periodic checks. And so to obfuscate this kind of thing or make it harder to find, you could instead dynamically load the relevant libraries with the networking calls and then find the functions at runtime and then call them that way. And then that way, when the cracker lists all the imports, they would not find they would not notice the networking functionality. Then finally, we have integration. You want to integrate your checks with important bits of code. This is to ensure that the license checking functions can't be easily knopped, which is a term of art for replacing the relevant instructions with no operation instructions. And some examples would be integrating your license checks with a file read, integrating with prepare. You're going to want to inline all these checks when possible. And then finally, we have frustration. And we hope it's the cracker who's frustrated, but it might be you the nth time that your plugin gets cracked. And so in light of that, we will talk about our last topic, which is how to post-mortem a cracked plugin. So if I pull up my terminal real quick, I can take a look at we can take a look at the checker1 binary that we saw earlier. So if I list the files in this directory, you will see that we have both the checker1 binary and we have the patched version from earlier. And in this case, we're going to use a tool called rzdiff or r2diff. These are open source tools for comparing the hex dump of two different binaries. And so we will open both of them up, and you can see that we get a side-by-side hex dump that we can scroll up and down. And if we hit the N key, we can seek to the first difference, which in this case is a single byte where we changed a 1 to a 0. And this is earlier when we changed the compare rex 1 to compare rex 0. So if I pull up my slides, in conclusion, I hope that you learned something useful about license checking. I hope that you have a better idea of the mistakes to avoid when developing your own copy protection, and I look forward to your questions.
Thank you, Chase. Any questions from the audience? Or
hello. I was wondering what your opinion was on just sort of not really copy protection in the secure form, but just things like nag screens, so making the copy protection not irritating for legitimate users, but just something that somebody who's maybe using it for free for a while thinks, oh, well, you know what, actually, I've used this for a year. Maybe I should buy it now. Something like that. What your opinion is, I just wondered.
Yeah. I talked a little bit about this at the beginning. I think you definitely need to evaluate your specific situation, the kinds of users that will be using your software, before you can know whether or not a secure license checking scheme is worth investing in. Especially because a lot of audio developer shops are small companies with a few people, and copy protection is not something that's already investing in. So I think nag screens are definitely a good option. If your software, if it's something like Contact, right, you probably don't want to just do nag screens. But if it's something smaller, I think that's a reasonable alternative.
So I wonder what your thoughts are on something like offloading license checking to a dynamic library like a DLL, but then having that binary code signed and doing like code signing checks on the DLL before you call into various symbols that may be multi-checks and things like that. Just code signing didn't come up in the talk. I just wonder what is it easy to bypass code signing checks?
Yeah. So I think that's a good way to simplify the integrity checks. The main downside is just that the license checking code is all going to be in the one file in the DLL. I assume, based on the way you described it. And so it's going to make it, once the cracker realizes that's where it is, then they will have significantly, the amount of code they need to look through will have significantly narrowed. And so it'll probably be a lot easier to reverse engineer that DLL because it's really small compared to, if all the checks were spread diffusely and hidden throughout the binary, it might be harder to identify. And so you could mix both of these. Another thing you could consider if you're using a DLL like that is it might be easy to encrypt it, like encrypt the DLL itself on disk in addition to code signing it. If you encrypt it on disk and then decrypt it at runtime before you load it, either in memory or on disk, then the cracker can't just, take the file and disassemble it because it's encrypted, right? So they'd have to do something more complicated, like, use a debugger to, get the program to the point where it's loaded and then dump the memory so that they have the decrypted DLL. So that's just another idea relevant to that.
Thank you. We have a question, online question from Ken. In the binary diff of the postmortem, how would you determine the code point of the change?
In the example I showed, or with the tools I showed, it's just a matter of hitting the N key to search for the next change. And you wouldn't necessarily need to use R2diff like I did. There's a variety of hex dumping tools you can find online that will do something similar.
Okay, another question for the audience.
Hi there. So you've said that no scheme is going to be foolproof. So how would you evaluate the kind of trade-off between the number of developer hours you'd put into designing a scheme versus how much time that's going to buy you?
Yeah, I think this is a tricky question. I think for the average company, probably what you want to do is, if you're not going to pay someone like Pace, is to have a relatively simple scheme that avoids the basic errors that I talked about. I think a lot of people will have like just a plain public RSA key or something embedded in the binary. And because this is super common, crackers in 3 or 4 minutes usually will be able to replace the public key with one they generate, and then they can forge licenses that the software will detect as valid. And so I think avoiding doing a scheme that's so simple that the cracker's seen this 30 times and can crack it in 5 minutes. I think it's, for most people, you want to make your scheme a little more secure than that. And making it a little bit more secure means it'll take a lot longer to crack it. Usually there's sort of a non-linear trade-off, I think, between that little bit of extra effort. Certainly an expert cracker will probably still be able to bypass it, but there aren't very many of those. And so I think that's what I think about the trade-off.
Another question?
Thanks for the talk, very relevant and interesting. So I've recently just done an obfuscation step on the public key that's stored in the plugin quite proudly. But then I realized I was trying to check for the public key in the binary, and I realized I don't know how to do that. So I know you showed us how to do that, but are there any sort of online resources that we can look at for similar tools like you've shown us, so that we can, maybe do some of the steps to try and crack our own plugin, or even just a few little checks to make sure that it's not too obvious?
Yeah, so one of the survey utilities I use is just the strings utility, which you'll find on any Unix system, right? Any Linux or Mac system. And there's an equivalent on Windows, I believe. And so that'll just dump all the strings. And so I'm not sure how you did the obfuscation. If it was just splitting it into parts and mixing it around, then the plain text strings will still be in the binary. If you've encrypted all those bits, then you can verify that actually succeeded by dumping the strings and making sure that you don't find them anywhere. As far as online resources, I think there's a lot of sort of intro to reverse engineering tutorials. And I'm not sure which ones to point you to, but that's something you can Google.
Last question from the audience. Okay, so we have a last question online. What's your view of having an easily crackable scheme to actually drive new users into buying your product later in life?
I think this is potentially a good option. What I see as kind of the best case scenario is if you have the incremental checks, like I mentioned, then someone might have a cracked version for a while, get used to using it. It becomes part of their workflow. And then later they get a demo pop up because there was, a check that's rarely triggered, found that the license they had wasn't valid or something like that. And I think in that case, you create an additional incentive, even more than what you're talking about, for someone to buy it.
Last question.
It's not a question, it's just something that I experienced many years ago. I had a cracked version of Ableton version 3, which worked great for about a month and then suddenly stopped working. And I'm pretty sure that there might have been something in there. And then I went and bought it. I think they had something similar like what you've just described.
Okay, thank you, Chase. Thank you really much for this talk.